So, as I said before, please write your name on the attendance list in the agenda that I'm sharing. And also you can add topics to the miscellaneous section. As a recap, on the last meeting, Josh Negret discussed about integrating a micro-ROS gripper with MoveIt. Wait a minute because, sorry. Okay, sorry. He showed how to connect micro-ROS microcontroller with the ROS2 control hardware interface. And for today, we will have here Yasushi SHOJI, co-founder of CEO of Space Cubics, and he will introduce us to the world of the Zephyr modularized version of micro-ROS. This approach eliminates the need for Colquhoun or AIMENT, offering a simplified experience. And also is here Russell Joyce, a robotics and embedded system research engineer at Microsoft, and he will provide a concise overview of Microsoft research project Silica. Russell will show us the power of ROS and micro-ROS to develop prototype robotics for the next area of data center storage libraries. So, Russell, if you want, I'm going to stop. Okay.
Okay. Hopefully my sharing will work okay. It's the first time I've done this kind of presentation in Meet, so hopefully it will all work. There's quite a few videos, so hopefully they'll come across okay as well.
Okay.
So yeah, welcome to my talk about the robotics we're working on at Microsoft Research in Cambridge, in the UK, to develop the next generation of storage libraries for the cloud as part of Project Silica. So Project Silica is a research project, which is a collaboration between Microsoft Research and Azure Storage. And we have a very varied team working across disciplines on everything from fundamental physics to systems design over a completely new storage media. And then somewhere in the middle of that, we've been building some pretty cool robots using micro-ROS for managing the storage in our proof of concept library, which is what I'll be talking about today. So a quick overview of what I'll cover. I'll give a brief introduction to Silica, very brief, just to give some context to why we're building the robots, and a bit of context on how archival data is currently stored in data centers. Then I'll go on a bit more detail about how we think future storage libraries might look, and also how we're using ROS and micro-ROS to build our proof of concepts. And then finally, I'll mention a few things we've learned while using micro-ROS along the way, which will hopefully be useful insights. Right, so to begin, some quick background on Project Silica. So it's been a project for a few years now. So today, the lowest cost option for long-term storage in data centers is tape. But tape really isn't great. Like any kind of magnetic media, it degrades over time. It's expensive and unsustainable to keep in the controlled environment they need. And they need refreshing every few years, which is a pain and expensive and not very environmentally friendly. So that's where Project Silica comes in. It's our potential replacement for tape in the cloud, which will hopefully help us cope with the ever-increasing storage demands that we're seeing going into the future. And the idea is based on new physics and completely new media, writing data into square platters made of fused silica glass, which are around the size of a CD. And then because of the way we write into the glass, we can achieve very high densities, end up with a storage media that lasts hundreds or even thousands of years without any kind of degradation. And I could really talk about the technology behind it for hours, and it's very interesting. But so that I have time to get onto the robotics here, I'll just give a very quick overview to sort of show why we're building these robots in the first place. So yeah, a quick overview. This animation shows how the data writing process works. So you can see here the silica platter is lying flat on this bench, and the laser is pointing down at it from above. And hopefully the video is playing okay. So it's scanning the laser across here, and during the scan, the laser is turning on and off very fast, which creates this pattern of data within the structure of the glass. Each pulse is on the order of femtoseconds, which is 1/1,000,000th of a nanosecond. And each pulse leaves behind one of these small fissures we call the voxel. And then millions of these are built up in layers by focusing at different levels. And then data is written once across the entire platter, causing a permanent change that can't be modified or overwritten, which is key to our design of the library. So that's the writing process. But how the data is read back is quite different. So in this image on the right here, that's what you'll see if you focus a microscope into the glass, or at least a render of what you see if you focus a microscope into the glass at a certain layer. So we capture a bunch of these images to reconstruct the data from the glass. The different colors here represent the data that's encoded in each of these voxels. The optics focus through and basically scan up and down across the platter as we need to read the sectors that we need. And it's a bit more difficult than it looks as well, because these are incredibly small. And then we pass these images to some machine learning algorithms to analyze it and decode the data, which is also a very interesting topic that I won't cover any of today. But yeah, looking back at the technology we're trying to improve on, so tapes. So how are tapes currently stored in data centers? It's pretty awkward because they need a constant temperature and humidity to keep them in good condition. And that, combined with the fact that tapes don't really last very long, is what really designs the design of today's tape libraries, which are deployed as one big monolithic unit of tapes, drives, robots, all in one construction. There's been very little innovation with this for a long time, and most just use these kind of fixed gantry robots, like in this video here. So these robots just move along in this narrow space, move up and down on rails, but it's all very centrally controlled and very fixed and inflexible. And one big problem with this is that if any part of the robot breaks, the whole library has to be shut down and serviced by a specialist engineer. You can't access any of the other data while that's happening. But because Silica doesn't have the same requirements as tape, and because we've moved on a long way since these gantry robots and the tape libraries were first developed, we're looking at ways we could rethink this for how Silica platters are stored in the data center. Yeah, so what can we improve on when designing the storage library then? So Silica platters last for a long time, which is the biggest difference with tape, which practically means the lifetime of the data center. So importantly, we want a library that can match that. We also want a library that can service modern cloud workloads, which look quite different to what tape was originally designed for. And one great thing about doing this research at Microsoft and collaborating with Azure Storage is that we can look at real usage data from our cloud services to make sure we're building a system that can actually handle this. And sustainability is also a key concern. We want to keep the energy and material costs as low as possible over the entire lifetime of the library, so that there's minimal environmental cost to storing data for a very long time. And finally, in order to build a library that works well for customers and the people who run data centers, we need to maximize the uptime and availability and minimize the time it takes to get the data back for people who need it. And to achieve this, our design has 4 key properties. We separate the deployment storage, writers, readers, and robotics, so that the storage can remain in place while other components are upgraded over time. The separation also means we can scale things independently depending on workloads. The shelving that holds the platters is completely passive, uses no energy, and we limit the power and networking to the parts of the library that contain the readers and writers, and only that. And the most interesting bit here, and what I work on, is that we deliver the platters around the library using these untethered, free-roaming shuttle robots, which I'll go into more detail about shortly. So to show how this looks, this render shows the concepts of the library, with the writers on the far left-hand side next to a big a rack of readers. There's, I think, 10 of them vertically, and then the rows of storage shelves going up to the side. And then between these rails running along the front are the platters, which are held vertically a few millimeters apart. And this arrangement is what we call a panel, which is one contiguous array of storage along with the readers and writers that can service it. But one thing that's missing from this view, you'll notice, is the robots actually move the platters around. So how might they actually fit into all this? So here's the same panel, but we've added some robots on and zoomed into the rack of readers at the end. So here's one of our shuttles, which is about to take a platter that's been ejected from a reader and place it back on the shelf where the platter needs to go. So the shuttle robot picks up the platter, moves along the rails, and then ungrips and flips downwards to a lower shelf. So the combination of these two movements, the horizontal and the vertical, means we can move the shuttle to any position on the panel, and it can access any slot in any reader. The shuttle then here finds the right slot, places the platter, and moves off to complete the next task. And as you can see, the number of robots can scale. So we've got 5 in this render, but the number can increase or decrease depending on the library and the conditions. So now you've seen the robots in that video. Here's a bit more detail about how they're designed. So the main goal we had was to make something that was independent of the rest of the library, but where any shuttle could still deliver any platter to any reader on the panel. And to achieve this, the robots are independently powered. They currently have a LiPo battery in them. They communicate wirelessly. We're currently using Wi-Fi for this. And they have both this fast horizontal and this ability to climb up and down vertically between rails movements, meaning they can travel anywhere they need to. And the robots are also fairly small and simple, which makes them relatively cheap to manufacture, and they can easily be taken off for servicing or upgrades. And when something inevitably breaks down at some point, it only blocks a small part of the library, and only for a short time, as a technician can quickly come and take it off, unlike a tape library where it takes down the whole system. Yeah, so I showed you the animation before, but in order to see how feasible a library design like this would actually be, we built a proof of concept library in our lab in Cambridge, and to test out our ideas, which is where micro-ROS comes in. We started by modifying a bunch of server racks with some custom rails and shelving. At this point, we've gone through a few iterations of robots on top of that. But to give an idea of scale, this is 10 standard server racks. So it's about 6 meters long, 2 meters high. And then we filled it with 6,000 squares of plastic, which took some time to construct. So before I talk a bit more about the architecture and what's running on the robots, I just want to show a short video of the robots actually, the real robots moving around. So here I am placing a shuttle on the rails. The shuttle then closes its grippers, and as soon as it's engaged, it registers with the central control system and is given a command, a micro-ROS action, to drive off and perform a task. So as much as possible, the shuttles perform this fast movement horizontally, where they go past hundreds of platters in a second, but sometimes, like here, you need to change shelf, and they do this vertical movement. The vertical movement also means the shuttles can move out of the way of each other. So you can see here, the shuttle moves upwards, and the other one will pass along underneath. And also, in case the shuttle breaks down, this design could even drive on just one rail. So this one is getting past this bottom shuttle, which is broken down and where it needs this shared rail still. As we filmed this video last October for the Microsoft Research YouTube channel. So the video is there, a longer version of this video, and on our website and things if you're interested in seeing more footage of these robots working. Yeah, that video showed one iteration of our robots. But we've actually made several during the development process to try different ideas. So there's one on the left. It's a very early model that was made just to test the vertical climbing. The middle one added the horizontal movement, which is an earlier version of what was in that video. And on the right is our latest version, which is rebuilt in aluminium, has some more powerful motors, and most importantly, it has the picker on the side, so we can actually handle the platters. But one core thing along all these prototypes we've made is that we've used micro-ROS on a microcontroller on them. So we like to iterate on designs quite quickly here. And one way we've managed to do that is to keep the same core controller throughout all the iterations, which is an ESP32 running FreeRTOS, and then micro-ROS to integrate with a wider ROS system. And then each individual model has a load of custom firmware, hardware, electronics on top of this to achieve it. And yeah, given this is a ROS meeting, I should probably go into detail about how we're using ROS. So this is a brief overview of our software architecture that we're running on the robots. So as I mentioned, we're running micro-ROS plus a load of other firmware on the SP32 on each shuttle. And then this talks to a number of ROS2 nodes and other software spread across a couple of PCs running either Linux or Windows with WSL. And we're currently using the standard micro XLC DDS micro-ROS agent for communicating with the shuttles. I briefly experimented with the embedded RCPS at some point, but found this to be more, the way we're using it here is to be more stable, and running the agent isn't really a problem in our lab setup, at least. So each robot registers a single node in the ROS network. We combine this with a number of supporting nodes on the PC side into one namespace per shuttle, which is very useful because it allows us to scale to many shuttles without having to worry about anything clashing between the namespaces. So one great feature of ROS2. And then we also have a few nodes in the global namespace to connect everything together and provide services like describing how many racks and shelves are in the library, for example. And I think at this point, we're pretty much using everything that micro-ROS has to offer in the shuttle firmware. There's publishers, subscribers, servers and clients, action servers, timers, liveness checking, time synchronization, all the services that have been put in over the time we've been using this. And it's all surprisingly robust now that we've ironed out the corner cases and sorted out our message handling and network and got everything stable. But as well, as much as we're benefiting from ROS for communication, this low-level control layer, for practical reasons of what we're building here, we're also trying to keep it as isolated from the rest of the system as possible, which seems to work quite well, actually. So, for example, all the micro-ROS code in the firmware is limited to a single library, and the micro-ROS ESP-IDF component makes it quite easy to integrate into a bigger system. And on the server side, our sort of high-level controllers for the scheduling and deciding which tasks to send to which robots and things are not written in ROS, and then there's a small ROS layer at the bottom for doing command and getting feedback. So before I move on to some more general thoughts about ROS and micro-ROS, I just wanted to have one last look at our shuttles because I don't know, I want to show off some videos of them. And so if I show this video showing our latest iteration of the shuttles, there's two of them running around here, much faster than before, thanks to some new motors. And they also have a picker on the side of them now, so they're picking and placing these platters. And then each command that's sent to the shuttle to move it horizontally, to do a pick, to do a place, is a ROS action sent from a controller on the PC. And here's a more close-up view of the picking a platter. So it goes along, finds the correct slot using some optical sensors, then extends the picker, pulls the platter in using a conveyor belt along the top and bottom of the platter edges. And then you can see that the platters are just sat in these slots at an angle, so gravity holds them in, and we've got no mechanisms that can wear over time and nothing active in the shelving at all. And finally, here's a close-up of the new climbing mechanism on the shuttle. So it just latches on rather than actively closing a gripper, which I just find to be a really satisfying thing to watch. So removing the gripper saves time on climbing, saves the motor, saves complexity and power. You can also see here the picker, how we keep it always facing the shelf each time. So it does 180-degree rotation back and forth, whereas the shuttle does a continuous flipping movement. So the picker kind of does this backflip here when it goes up between these two rails. Yeah, enough of our shuttles. So talking a bit more about ROS, I'm sure most people here already appreciate the benefits of using ROS to build a robot system, and all the great tooling that most of the time just works. But another big part for us was being able to leverage the communication primitives, especially. So mostly actions, which fit our model very well of telling the shuttle to move somewhere, getting constant feedback to the controller, and being able to cancel it from either side. But really, the best part of having micro-ROS available to us for all this was it allowed us to do all this with just a microcontroller. If it wasn't for micro-ROS, we probably would have had to either add some kind of single board computer onto the shuttles, or not use ROS at all, or hack something together to get the messages across to a ROS system on the PC side. And just having micro-ROS to be able to pull the shuttle into the ROS system that everything else was using for the monitoring and control was really valuable, and saved us a lot of time and effort during the development. And yeah, while it's been great having it as a tool, we've definitely learned some things over the last 2.5 years that we've been developing these shuttles with it. So we started building these shuttles at quite a fortunate time in the micro-ROS timeline, when it's getting just a bit more established back on ROS Boxy. And it's definitely improved in terms of stability and tooling since then. A lot of work has been put in, of course, on this. It probably didn't help that back in the beginning I was running it on multi-core FreeRTOS before that was actually supported, which didn't help with stability. But yeah, it shows how that was a great addition of multi-threading support a couple of years ago. But still, one thing that will always differ from standard ROS running on a real computer is having to manage everything much more carefully. Like if the Wi-Fi breaks, it's your responsibility to tear everything down and bring it back up. There's no OS doing things for you. And while built-in things like the liveness checking can help a lot with dealing with sessions that are disconnected, we found that using a unique fixed client key for each device also helps a lot when you have lots of micro-ROS nodes in the network, when you need to recover from a problem, so they can re-register with the agent nicely. And we've also found that it integrates well into a bigger system, and is useful even just for the robot controller communication layer. And yeah, two more kind of practical tips, I guess, that we discovered along the way are pretty much just related to memory management, which is, of course, always a much bigger concern in an embedded system than in most systems. So firstly, one thing that's obvious to us now, but caught us out in the beginning, was that actions need to have enough static resources allocated to them. I think the slightly confusing thing was that because of how actions are implemented, you don't reserve the memory for the action itself, but rather for the services, publishers, and other things that they use underneath. So that's something that's definitely worth remembering when using actions, and requires a bit of deeper knowledge of how ROS works than if you were doing the same with RCL-Pi, for example. But it works very well in the end, and the action interface is great. And secondly, good memory management is also key for messages. So micro-ROS now provides some nice help functions with this, of course, but it's important to actually use them, and or at least make sure that any messages have enough memory allocated to their data. I found, especially when coming from using ROS in Python, it's easy to forget that you need to do memory management with messages. One place that caught me out especially was changing a fixed length array to a bounded array at one point in a message definition, where on the Python side, nothing changed at all in the code. But because RCLC implements bounded arrays as a pointer, whereas fixed length arrays are stored as an array in the message struct itself, the interface change made the robot very unhappy until I explicitly gave the message the memory it needed. Yeah, and on that note, I just wanted to thank everyone who's contributed to micro-ROS over the last few years. It's definitely been a very useful tool for us, and it's great to have a proper way to integrate microcontrollers into a ROS system, rather than using dodgy workarounds or just not being able to use a microcontroller at all on its own. And yeah, thank you for listening to my talk. I hope it's been interesting to learn what we're working on, and how we're using micro-ROS within that. This is our project website, aka.ms/Silica. If you'd like to know more about our robotics or the wider project, there's more information there. Or feel free to get in touch with me or any of the team if you want more information. Yeah, thank you. Please let me know if there are any questions, if we have time for questions.
Any question?
I mean, of course, first of all, thanks a lot for your presentation, and to see micro-ROS in this very interesting and funny robot. So it's interesting to see how it climbs up and down. And I have a couple of questions regarding the robot. As you know, you have these racks of individual pieces where you store the data. I guess needs to be very precise. And I was just wondering, how do you achieve the precision for the localization or in the robot? And do you need that? Do you achieve it with the support of particular sensor fusion, or do you need real-time capabilities of the micro-ROS stack? I mean, this was my question. I mean, how do you achieve this high precision?
So yeah, the way we're doing this currently is, so we're not using micro-ROS or any sort of communication with the PC for this. It's all on board, and we sort of do a coarse-grained location based on just an encoder that's on the output motor. So it drives left and right. You can just about see in the top of this picture here, there's a pinion that goes down onto some racking on the rail. So that's what drives it left and right. And then we can work out with an encoder on that how far that's turned and get a rough idea of how far it's moved. And then we combine that for the fine-grained localization to line up with the platters with a couple of optical sensors that are on the picker that looks forwards. So then from the end of each rack, it counts a number of slots. We've got some markings with some holes cut in them, and the optical sensors, there's two next to each other, travel past that, count the slots along there, and then stop in front of the right one based on how far it's counted from the end of the rail, and then it can center on the slot like that. And this might not be how it's done in a real system. I'm not sure this would be robust for running for decades, but in terms of our prototypes, it's turned out to be good enough for getting the right platter doing this pickup.
And with what kind of frequency are you controlling your motors?
So we have the main controller on the shuttle, I think, runs like I think 20 times a second or something. Nothing is too fast or too real time. It doesn't mean it's implemented in the best possible way currently. And then yeah, that updates the status on the motors. Then each motor itself has its own microcontroller, which is completely separate in the system, which is doing the like trapezoidal trajectory movements and things.
And I have just one more question, and then I can leave, of course, to the other participants. You mentioned on one slide that the lowest and highest layer is where you don't use ROS. So what do you mean by the lowest layer?
So by the lowest layer, I mean just the things on the robot that are like the controller itself. That's so the messages come in from outside, and we try to translate everything from like the ROS message domain into structures that we can use in the rest of the robot that don't know about the micro-ROS side. So everything's then managed in like the controller task and the controller components without necessarily knowing that micro-ROS is there. So that if we then had to replace it with a different communications layer or something, we could not that we're planning to, but
okay. So but basically, so then the low level controller is not, let's say, a part of micro-ROS with a timer or something, but you have a completely separate thread that then kind of shares some memory space, and then where you just hand over the data, like in ROS2 control, which have a similar concept where you have the messages coming in, and then you have the controller plugin, and all that stuff runs then a real-time thread. And that's completely separated then from the rest of the ROS system.
Yes. Yeah.
Okay. Thanks.
Okay.
Okay, Pavel.
Well, hi. I have to say that I'm thoroughly impressed by this project. This is fascinating to watch. And my question would be, what do you think is the time frame for when we're going to have the system? Because I need one now. DVD and CD collection. I already see my...
Yeah. I don't think I can comment too much on that side of things.
Big again. I mean, I know it's 10 years or 5 years or...
I'm not really sure. I don't know. There are plans, I imagine, at levels far higher than me.
Okay.
I'm just making the
what about the other aspect of it? Are you planning to, I mean, is this open source, or can we, because literally I only use it for my CDs. I mean, I have such a stack of those, and it'll be fantastic project.
Yeah, it would be cool to release that sort of thing, I guess. But
does Microsoft have any plans for that, or is it just gonna be a research project?
Just a research project for now. I don't. We have no plans for open sourcing anything. I don't think, unfortunately.
Right.
But yes. Again,
I mean, fantastic. I mean, it brings back memories of watching the Star Wars with all these storage arrays. It's happening. Thank you.
Thank you. Okay, Brian, I think has.
Yeah, thanks a lot. Yeah, it was a very interesting presentation. I just want to know if you could say a few things about kind of the coordinating between the robots, because I see sometimes they share a rail, so the one has to kind of move out the way of the other one, and then I guess move back again. I was just curious if you have a few things to say about this kind of coordination between the robots.
So there's something we're actively working on at the moment is sort of the whole scheduling side of things. So that's a very interesting problem in itself. And yeah, they do have this shared rail, which is one limitation of this system, where they flip between the rails because they're always holding one common rail. But yeah, there's lots of possibilities in that space. At the moment, everything's controlled centrally, because our system, I don't think, is big enough to worry about turning this into some sort of autonomous swarm or anything. But yeah, currently everything is kind of scheduled from a central computer that's deciding the routes that the robot should follow based on the platters that need to come in, that need to be dealt with. Yeah, I don't have too much more information on that at the moment, unfortunately.
Okay, thanks. Yeah, the fact that it's centrally controlled makes a lot of sense. But yeah, thanks for that.
Okay. Oh, and as Marco has just pointed out, as Marco is also working on this, he just put in the chat that using a MapF algorithm for some of the scheduling of the robot movements.
Okay, thanks, Marco.
Okay, so I think that there are no more questions. So thank you very much, Russell. Very interesting, your little robot moving. It's amazing.
Thanks.
Yes, thank you very much. Okay, so now is the turn of Mr. Sijo. Are you here? Shoji, Yasushi Shoji, are you ready? You're on mute.
Okay, how about that?
No, better.
All right, great. Let me share my screen. Hold on.
Yes, I think that Russell has to stop. Yes, now you probably will be able.
Okay.
Okay, perfect.
All right. Thank you for having me here. So interested in talking about the stuff I'm working on. It's not like the robot things, but I'm actually working on the micro-ROS itself, or actually how it packaged it. Okay. Let's see. Oh. First of all, who am I? My name is Yasushi SHOJI, if you prefer the longer one. And I've been working on softwares, and a few years ago, I've worked on some drones for ISS, International Space Station. And I have founded with my friend a company dedicated to designing and building a single board computers for spacecraft. And I've been doing the open source development for like, I don't know, 20 years or so. And I just started to learn ROS and robotics. So I'm not by no means any robotic guy or ROS guy. So please bear with my poor skills about the robot and ROS things. And currently we are working on this kind of robots. This one is for Fukushima. That's a nuclear. We had a nuclear disasters in Fukushima in Japan, and we're trying to automate a couple of things in the place, and that's what we are working on. But it's still so early stage, and it's just parts are just moving using the micro-ROS and stuff like that. So it's just prototyping and stuff. So it's not like the cute robot that we just saw it. Okay. Okay. So today's talk is the fourth check mark here. This list is taken from micro-ROS webpage, and micro-ROS says that it's support generic build system, but my talk is like specific to Zephyr real-time OS. So it's just a different way to pack those repositories for micro-ROS components, and I'm sure that it's pretty good for Zephyr users, but I'm not sure others like FreeRTOS or any other platform that micro-ROS is supporting. So, and before diving into micro-ROS for Zephyr, there is of course official support for Zephyr and micro-ROS, and it's so easy that people can just follow the command line, just type in a command and then test the lots of samples in there. So it's so great. But if it's so great, then why did I work on it? And I just wanted to reduce the it's called a cognitive load, and also want to fill the gap between those tutorials and the build environment that we, as in Zephyr users, use every day. And I also wanted to utilize a lot of the tools that Zephyr already provide to users. And by reducing a cognitive load, because I'm not the ROS users, and well, I do program ROS on the PC, that desktop. So I do use ROS2 commands, but I'm not familiar. I wasn't aware of the ROS micro-ROS setup command, the subcommand that micro-ROS provides. And I was a bit of a hard time what's going on because I was not familiar with that subcommand. So that was a little bit of a load in my cognitive memories. And I also wanted to share the gap between the first tutorial and the real applications, because the tutorial is so great. You can just test the ping and all the agent stuff. And now, once you finish that tutorials, I have no idea how that thing should integrate to my application. So I have to dig into the subcommand and find all the shell script and stuff like that to figure out what's going on underneath. And with those tutorials, I couldn't use the tools that I already had with Zephyr environment. We use a command line tool called West to fetch the updates and also build the images and flash the images and also run the debuggers. And ROS on PC use VS tools to fetch the update and Qualcomm to build and install the packages. And we now have with ROS, the micro-ROS setup to flash the image, and also you have to use a ROS2 to debug the final application. So to summarize it, I wanted to remove everything that I don't need, and I just wanted to take the core part of the micro-ROS so that I can easily combine whatever we have already in the Zephyr and also the core meat of the micro-ROS to the Zephyr. And that answer, I found it on the ROS webpage already. And that diagram shows that micro-ROS is combined of the client library and the middleware. And also, I found that I don't know. I mean, I'm not the ROS guy, so the message is pretty big part of the ROS. So I just added it to the list of it. And I didn't think that a ROS2 agent is not a part of the micro-ROS, because I mean, you need that agent to talk to the micro-ROS, but you can build and test it on a PC. So I don't think that should be integrated in the Zephyr environment or any other real-time OSs. Okay. So to introduce the Zephyr modularized micro-ROS, I just took a couple libraries, the client libraries from the micro-ROS and the middlewares and the messages, and just pack that things in the other way, which is called Zephyr modules, and integrate that as ordinary Zephyr modules. And you can remove that ROS2 subcommands to build and test micro-ROS on the Zephyr environment. And this one is for people who don't know about the Zephyr. If you know already, you can just skip that. But Zephyr is a project name, and it has many stuff in there. And I'm just picking the 3 out of it. And Zephyr, the real-time OS, and Zephyr build system, and Zephyr's meta tool, it's called West. So I'm just briefly introduce these things. Yeah, real-time OS is just yet another real-time OS system within the C. It's under the Apache license 2, and it's under the Linux Foundation. And the Git repository is at the GitHub right there. And the build system is a bit messy or complicated, as I said, because the Zephyr supports many boards and hardwares, and many stuff has to be figured out on the runtime, or not the runtime, the build time. So many configuration stuff, hardware stuff, it has to be combined at the build time. The Zephyr build system is based on the CMake, and actually many CMake file is combined to build one large CMake project centered around your application. So that means that you don't need a Mint CMake to register your packages, to retrieve the information and set the dependencies with it. We can just use plain built-in function, CMake function, to describe the dependencies between the libraries. Zephyr build system also has a device tree support. That's Linux also use it, so many people these days already know about that. And it also supports the kconfig menus to configure the system. Many parts of it, like libraries, kernel, subsystems, and hardware can be configured from this kconfig. The implementation that Zephyr uses is kconfig lib. So it's not the It's not the same one as the Linux kernel, but the implementers of kconfig lib said that it's implemented all the features, including all the bugs in kconfig in the Linux kernel. So it's pretty same thing. And it supports the menu config at the the left image, and GUI config on the right. And the final thing is the West. This one is the Zephyr's called meta tool. It's not the build system. It's more like VS Tools, Cocon, and micro-ROS setup combined in one tool. So this one is like a subcommand comparison table. VS Tool doesn't have a workspace stuff, but the West is workspace based. So West has an init workspace subcommand. VS Tool use a pull to fetch the changes from remote repositories, but the West use update. And VS Tool use export to print a list of the repositories, but West use a list. Both tool has a diff to show what change each repository has, and also has a status. And the custom is called for all in the West. And the Cocon is usually used to build packages under ROS environment, but we use a West build to build the final images. West also has a test command. Zephyr has a lots and lots of tests, and the test runner is called the twister, and West also wraps the twister in there. Cocon has an info and a list subcommand, but West doesn't differentiate the package and repository, so we don't have those subcommands to show package informations in West. West also has a sub command. You can specify the target for the build command. If you target the menu config, you're gonna see that the menu config that I show in a couple slides back. And also has a RAM report target, which shows you the all the RAM usages of each object. And it also has a ROM report, which one, oh, I'm sorry, it has a typo. It's a ROM usage, it's print ROM usages. And it also, West can also build a final flash, the final images, and flash that image, which the micro-ROS setup does. And it also has information about the supported board, so you can print all the boards that Zephyr currently supports. And it also has a debug and a debug server to launch debuggers or debug server, so that you can attach your IDE or your GDB to the debug server. So that's Zephyr and West. So we don't actually the Zephyr and the West combined. I think we can cover what the ROS2 subcommand is providing. So I like to use Zephyr or West command instead. And that libraries or the repositories that I take from the micro-ROS is listed there. The client library is RCL, RCLC, and RC utils, the middlewares, RMW, and all the micro. How do you pronounce this? Micro XRCE DDS? I don't know. I don't know how to pronounce that, and many others. And the messages, you can add many other messages and the custom messages as well, and IDLs to convert the message to supporting libraries. Okay, to be a Zephyr module, you have to have a directory in the file in there, which is a Zephyr module YAML file. That file is a key file that Zephyr build system will find can instantiate a lot of things to make it buildable. And additionally, you can add repository the west YAML file, which tells the west command to manipulate those repositories. Actually, those modules and the project is different, but for this presentation, you can think that module and is the same as a west project. It doesn't really matter right now. So to make LCL package or the repository as a Zephyr module, you need just 5 lines here. Add a module file, module YAML file, and then add build tag, and just say that CMake is external, and dependency of this CMake is LCUtils and LCL interface. One more example is the altmw. It's kind of the same thing. Dependency is less than the others. It only depends on the LCL utils. So this file is the only thing that you need to make a repository Zephyr module, because it says that CMake is external. So the build thing has to be some other place, and that thing. Well, wait a minute. Yeah, I just said that it just says a CMake is external, and also you have to specify the dependencies and make sure that this one is not the build dependencies, but it just only means that CMake process all the dependencies. The package dependency or the build dependency has to be specified in the CMake. Okay, so this one is the meta packages that I created, and this one holds all the CMake list text for all the micro-ROS modules that I have, that I integrated from micro-ROS and ROS2 and others. And this one tells the build system to build each modules and collect public header file directories from each modules and give them to application so that application can include any header files from those directories. And it also create a target which collect all the static libraries from a library so that the final image can be linked against it. And this one is the example of CMake list for micro CDR. This one, I think this one was the simplest one that I have. And if you know the CMake, it's pretty straightforward to read it, I think. But I'm using couple Zephyr extension functions. The second line has Zephyr library named. That one is more like target. Wait a minute. Target library, I think. And this one creates the library named ROS to micro-CDR. And lines after add include directories for that target. And then you add source code as usual, and then a couple defines for version numbers if you need. And CDR needs the system endianness. So just take that machine endian and set that CDR big endianness or the little endianness. And then just write that information to config.h, and that's about it. And the Zephyr build system will just build it. Oh, because you could use the original CMake file to build for the Zephyr if we can coordinate that upstream. But I was too lazy to do that and just wrote it, copy paste it and here for specific to Zephyr. And the other example is a micro XLC EDDS client. And this one also creates, you see mouse moving? Oh, here you go. This one also create the library called ROS to micro XLC EDDS client. And also include a couple of directories for include here, and add source codes in here, and define a couple of variables. And you can set options like here, but this should be moved to the kconfig because we already have a kconfig. I was just too lazy to left there. And if you have some options that user don't need to set, you can just set it in the cache right away. And interesting thing here is that the last line, except the endif, you say in here that this micro XLC EDDS client depends on the ROS to micro CDR, like this. This is the build dependency. CMake project will take whatever the target, the ROS to micro CDR has, and link it to or take the header file information or anything that set to the target for this micro-ROS, no, micro XLC EDDS. And the final line is the one you need to do that. Okay, moving on to the standard message. This one is a bit different because you have to use the IDL to generate the C file, header file, and something like that. So in order to do it, just gather all the message file you have to generate. No, you have to use to generate your file. And then there's a function I created. It's just simple name. I should have some prefix to differentiate with the other file name, but it's called the gen files right now. That's simple enough. It takes 2 inputs, the directory, message directory, where to find the messages, and the files, the list of the files that we just created. And it will create or generate header files and the source file and set those files in those out variables, headers and the sources. And we're going to use that headers and the sources in underneath. When you create the add custom target, you have to depend on the headers because you want it regenerated when the header changes. And also this one creates Zephyr library name with the function Zephyr library name, ROS to standard messages. And with that name, the target, you add the dependency of the custom target we just created, and add include directories and link libraries right there, and add sources that gen file generated, so that we can create a library out of those header file, not the header file, the C files, stuff like that. And in order to generate those source file and header file, all the IDL must provide a function. And we currently have ROS IDL and ROS IDL type support, and the ROS IDL support micro XLC EDDS. And the functions are called in gen files, and each message file or service file or action files will be generated by those IDLs. Because if you are using the ROS in a PC, there are many transport, so that many you have to generate many files for each how do you call that, each IDL. But currently micro-ROS only support one transport, so you don't have to find nothing but just one IDL. Use the one IDL to generate those source files. All the information is under this Zephyr modules and ROS IDL. So if you are interested in, check there. And finally, to use this Zephyr modules micro-ROS, all you have to do is add this 5 line to your REST YAML file. Then it's gonna bring everything in and build it and link it to final images. Okay, that's about it. Is this time okay, or should I go to the demo, or is everything okay?
No, you can go. I think it's not going to take long.
Okay, okay. Let me stop this for now, and wait. Is there one? Nope. Wait. Oh, no. Okay. Do you see a screen? No?
I see you.
Okay. I don't know. I don't know why it doesn't work. Let me try again. Share. Is it coming?
I think that now, no, you again.
Oh,
Now we can
okay.
see your screen.
All right, great. Okay, so you see it, right? We need a workspace. Wait a minute, I already have a workspace. Okay, there's a workspace. The West need a workspace, so I just this one. And what we need is application directory. So you can just mkdir and app. Okay. What we need is the REST YAML that file. So it's still empty. And to have Zephyr hello world, that's things that you need. And also let's create a hello world here. And see, make directories inclusive name point. Okay, hello micro-ROS. Something like that. There we go, 0. All right. And you also need make lists. Oh, wait a minute. Do I already have it? Okay, that's about it. And because I don't have a Python the packages that I need, so I'm just use pip shell. Okay. And pip install libraries in this virtual env. Okay. And now what we do is REST build and specify, REST build app. build it. Whoa. So west. Wait a minute. What is this? Unknown command build. Do you need? Oh, I'm sorry. I have to clone the Zephyr itself. I'm sorry. Clone Zephyr. And west initialize the okay. West YAML. Oh, sorry. File name is different. Oh. There you go. And we fetch a couple repositories and let's build the application. Still can't do it. West CMake list app doesn't contain what? CMake lists text. What does it mean? Oh, where am I? Where am I? Oh, I'm sorry. That's different directory. Oh, I'm sorry. CMake lists. Ah. There you go. There you go. And we build it. Maybe I should just stop this. I don't know. First, I'm sorry. That I need a. Okay, good. All right. Now I can build the hello world. Now I wanted to integrate micro-ROS into this. And to do that, we can just open the main file and add a couple lines like about this and that, and also LCL like this. And I'm gonna just tell West to fetch the micro-ROS, which is like this, because the West has to get that repository we call West update, and it's gonna fetch all the modules that micro-ROS to Zephyr is depending on. It'll take a couple of seconds. And grab that, we can just, okay, no such directories. Why? Why? Oh, I'm sorry. We have to tell that we are using a micro-ROS, and also micro-ROS depends on the story we see. We have to change the project conf like that, and it should build. All right, that's it. All the warnings. This warning, I have to fix it, but a couple argument or some type is different than the others, so I have to figure out how to fix it. All right, that's how you integrate it. I'm sorry that couple mess. Now I can go back and a few more slides. There we go. Okay. Some future works that I want to work on. I want to fix that warnings that I show you right now. And also I have Zephyr transport already working, so I want to update or upstream to that. And I also want to upstream a couple Zephyr specific improvements and fixes that I have. And I also want to implement a couple of tests in the Zephyr test framework. Zephyr has a pretty good test framework. So I want to test that, test micro-ROS in that framework as well. And I also want to update or upstream reusable part of the CMake function that I have. And I also want to implement ROS2 subcommand in Zephyr shell. Zephyr has a shell, and that shell is pretty neat. And you can add a subcommand to it so that maybe like ROS2 topics or ROS2, I don't know, ROS2 has some command to list the topics and nodes and stuff like that. And maybe Zephyr shell can implement that features. All right, that's about it. Thank you for having me here, and thank you for joining my talk. Thank you. That's it.
To you, Yasushi. I think that Powell has the hand up. And maybe.
Oh, sorry, I left it on the previous question, but fantastic presentation.
Okay.
Thank you.
Okay. Any question to Yasushi? No questions. So, okay. So thank you very much, Yasushi, for coming here and for sharing your job. I think it's very interesting. And well, that's all. We are going to close here this meeting, and we are going to be back on September. So July and August, we won't be here. So thanks a lot and have a great summer. See you. Bye.
Bye. Thank you.
Bye.